We are working on applications of the derivative. I have introduced an applied problem for you. So far, I've went through parts A through C, and I have introduced part D to you. That's why I left the last video. We want the instantaneous velocity of the flea over 1 second, and so this is actually where the calculus part of this function fits into play. We know to compute the instantaneous velocity, we have to compute the derivative. So we know that the derivative is defined as the limit as h goes to 0 of typically f of x plus h. Our function here is h of, instead of x, we're going to use t plus h minus h of t all over h. And we know that we have to use notation for this. So since our function is h of t, the derivative notation that we should use is h prime of t. Okay, so let's get right into the steps of the derivative. The first thing that we like to compute is h of t plus h. We do that by plugging this t plus h into each part. We see t in our original function. So that gives me 4.4 times t plus h minus 4.9 times t plus h squared. So let me FOIL out that t plus h squared. Gives me t squared plus 2th plus h squared. And then distribute my coefficients. So 4.4t plus 4.4h minus 4.9t squared minus 9.8th minus 4.9h squared. Whew! Okay, now we want to substitute that into the fraction, the difference quotient. So we want to compute h of t plus h minus h of t all over h. So I need to subtract my h of t, which is my original function. Make sure to put that in parentheses to note that the negative goes to every part of the function there, and that is all over h. Okay, now let me distribute this negative, and let me cancel out some things. My 4.4t's cancel out, and my 4.9t squareds cancel out. Every term left has an h in it, so let's factor that h out, leaving me with a 4.4 minus 9.8t minus 4.9h. And again, that's after I factor out an h from all of my leftover terms here. And the reason that we did that is to cancel out with our h in the denominator. So that moves us to the third step of our derivative, which is computing the limit of when h goes to 0 of whatever we have left. 4.4 minus 9.8t minus 4.9h, which means we just substitute in 0 for all of our h values. Of course, that's going to become 0 and cancel out, so we are left with 4.4 minus 9.8t. So we have officially computed our derivative, so we are going to substitute in our notation here. h prime of t equals this here, 4.4 minus 9.8t. Okay, now if we want the instantaneous velocity of the flea after 1 second, basically we need to plug 1 second into our instantaneous velocity equation. So we need to plug this 1 second into our derivative equation. So h prime of 1 equals 4.4 minus 9.8 times 1, or 4.4 minus 9.8, which gives me negative 5.4. So again, what we just computed was the instantaneous velocity of the flea after 1 second. Or a different way this problem could be worded is at what rate is h of t changing after 1 second. So rate is the same thing as instantaneous velocity. Okay, we have an answer here negative 5.4, but this is a word problem, so we need a word answer. Now, we just computed velocity or rate, which means our answer should be something per something. Okay. In this case, what we computed was the height, so specifically in meters, compared to the time, so specifically the seconds. So, at the first second of this jump, the flea has a velocity or a rate of negative 5.4 meters per second. All right, the second part of this question then is it increasing or decreasing? So is my rate or is my velocity increasing or decreasing? Okay, well, since our answer is negative, that tells us that our rate is decreasing at this time. All right, let's go back and let's put this with the graph that we drawn in the first video to see how it fits in. So I have my graph here. I graphed my average velocity over the first 1/2 seconds in green, but now I just computed the instantaneous velocity, and I computed it when t equals 1. So if I look at my graph, when t equals 1, that puts me all the way over here. So if I were to graph this down farther, that would give me a point closer to this over here. Now, we came up with the answer of negative 5.4, which told us that the rate was decreasing. That makes sense on our graph because our flea is at the descend of his jump. Okay? Since he is going down on this portion of the jump, that means here our velocity is decreasing. So, of course, at 1 second, he's going to have a decreasing velocity, and specifically, the velocity was negative 5.4 meters per second. So now that we computed our velocity, or our h prime of t, let's move on to the next part, part E. So this part specifically asks, when is h prime of t equal to 0? Well, that's easy. We can do the math of that, no big deal. The harder question probably is what's the significance of that time? Well, let's do the math first, and then we'll fit in the applied part. We came up with h prime of t equals 4.4 minus 9.8 t. So if we want to know when it is equal to 0, we just do that. We just set it equal to 0. This is a linear or degree 1 equation, so I solve it by isolating my variable. So let me move that portion to the other side. So that gives me 4.4 is equal to 9.8. Divide by 9.8. And so that gives me that t is equal to 0.449. Okay, so the first part of this question is asked, at what time is h prime of t equal to 0? So specifically, the time is 0.449 seconds, and that is actually a rounded number, so I should change this symbol here. That's the first answer. And the second answer was, what is the significance of this time? Well, let's go back and let's look at the graph. And let's see, did we see that 0.449 any other place when we were graphing this? And we did. We actually saw it in our calculations right here. And that was when we were trying to compute the vertex. So 0.449 seconds is right here, which is actually the peak of our graph. And so if we're talking about the rate of our flea's jump here, on the very first part of the graph, the rate would be increasing because the flea is getting higher and higher and higher. The second part of the graph, we just said, is decreasing because the flea would be getting lower and lower. So at this part up here is when our rate is equal to 0. So that's when our rate changes in this version from increasing to decreasing, or it could also be the same thing from decreasing to increasing. So specifically, why is that important for the flea? Well, that's when the flea is at the peak here. So why is this significant? Because the flea is at the peak of his jump. So if we ever compute when our derivative is equal to 0, that's when the rate changes from increasing to decreasing or decreasing to increasing. This is where I'm going to stop this video, and in the next one, I'll come back and compute part F.